In this work, we propose task-driven implicit representations for automated design of LiDAR systems. LiDAR system design for 3D perception is a ubiquitous challenge across fields, including in consumer AR/VR devices, satellite scanning and remote sensing, autonomous vehicles, and in aerial imaging. However, LiDAR design is challenging for three key reasons. First, it requires navigating a high-dimensional, mixed, discrete continuous space, which encompasses things like sensor count, scan patterns, placement orientation, field of view, and temporal parameters. Second, these configurations should ideally be suited for the target application. A front-facing smartphone LiDAR should capture fine-scale facial geometry, whereas a distributed robotic tracking system should conform to the robot's workspace and kinematic constraints. Third, design should satisfy both physical constraints like size, weight, power, and cost, and user-specified design preferences, requiring rapid, constraint-aware design exploration. In this work, we propose a framework for computational design of task-driven LiDAR systems under arbitrary constraints. Through this work, we show first that LiDAR systems can be represented in a continuous 6D space. We then propose learning task-driven LiDAR designs as implicit densities over this 6D space via flow-based generative modeling. Finally, we synthesize physically realizable LiDAR systems by modeling sensors as parametric distributions in this space, which we fit over the implicit density via expectation maximization. Our first key insight is that all LiDAR systems can be represented in a continuous 6-dimensional design space. Specifically, in direct time-of-flight LiDAR, a pulsed laser emits short pulses along a ray direction. These pulses reflect off of scene surfaces and are received by a detector at a given time of flight. Thus, every LiDAR measurement can be encoded in 6-dimensional space as a design point, where each design point is comprised of a location, xyz, an angle, azimuth and elevation, and a time, tau, along the ray, which represents the point time-of-flight measurement taken along that ray direction. We can visualize a simplified version of this design space for a single 2D scene surface point, the blue star on the left. Each ray in the middle diagram represents a LiDAR measurement, which has a given origin, angle, and time or depth associated with it that allows it to observe the scene point. Then, on the right, we show that each of these LiDAR measurements are points in our design space. We can notice that single scene points create curves in design space, which represent LiDAR measurements which can all observe that given scene point. Building on this insight, we show that full existing LiDAR designs form discrete sampling volumes over point measurements in 6D design space. Later on, we find that this representation in design space allows us to not only evaluate existing LiDAR designs, but also synthesize new designs as volumes in our design space. Our second key insight is that we can pose the problem of LiDAR system design as that of learning task-specific implicit densities within this 6D design space. Going back to our simplified design space visualization, we can think about the points along the curve as points with high surface proximity. That is, these are LiDAR measurements that are able to map very closely to the scene surface. Extending this idea to physically grounded scenes, we know that LiDARs must also have high ray visibility. That is, the ray from LiDAR measurement origin to its observed scene point must be unobstructed, for example from self or scene occlusions. Ideally, for a given scene or task, we have a way of choosing LiDAR measurements and designs which are both high in surface proximity and high in ray visibility. To do that, we first establish a density evaluation metric, which allows us to evaluate the quality of each design point or LiDAR measurement for a set of scenes, which represent a task. This density evaluation balances these two key LiDAR design factors, high surface proximity and high ray visibility, to help us evaluate over a set of scenes how well suited a LiDAR measurement is for observing that scene surface. Importantly, we show in our paper that this evaluation metric is general enough to help us synthesize well-suited designs across tasks and objectives, including for 3D scanning, 3D object tracking, and object detection. Although we now have a well-defined evaluation metric for each design point, identifying and sampling from high-density regions for a given task is still challenging. To solve this problem, we leverage flow-based generative modeling, specifically normalizing flows, which help us to efficiently learn, represent, and draw high-quality samples from the high-density target distribution under task-specific scene simulations. Specifically, we begin with a class of scene simulations, for example, the 2D surfaces on the left side. Then we use normalizing flows to learn a mapping between an easy-to-sample base distribution, in our case a 6-dimensional uniform distribution, and our complex target distribution, in our case the distribution under our LiDAR evaluation metric for a class of scenes. This allows us to represent LiDAR designs as implicit densities, specifically as the mapping between tractable base distributions and our LiDAR design distribution. We therefore obtain a task-driven implicit density, shown in the middle panel, from which high-density design points can help inform the design of high-quality LiDARs for a given task. Our final key insight is that we can synthesize new LiDAR systems by modeling sensors as parametric distributions in our 6D design space and fitting these sensor distributions to our implicit density. Recall that we earlier showed that we can represent existing LiDARs as volumes in design space. Similarly, to generate new sensors for a task, we can represent sensors as parametric distributions within our design space. Then we can fit these sensor distributions to our implicit density via expectation maximization. In doing so, we enable the design of both high-quality and physically realizable LiDAR systems. Importantly, this LiDAR synthesis approach helps us easily incorporate constraints. For example, we can enforce spatial, angular, or temporal constraints by simply restricting the support of the implicit density. Alternatively, we can enforce constraints by clamping parameters of our sensor distributions. The ease of integrating various arbitrary physical and user-specified constraints is a key benefit of our sensor design framework. We evaluate our proposed technique in 6 experiments over 3 domains. We refer to our paper for the complete experimental details and results. In experiment A, we show first that we can design flash LiDAR systems for face scanning. Our design systems yield consistently improved mesh reconstructions compared to conventional LiDAR designs used currently in mobile scanning. These results highlight in particular that our proposed technique is capable of conforming to variations in scene and surface geometry. Importantly, we show that we can generate new LiDAR systems for face scanning under various constraints. For example, on the left, we visualize mesh reconstructions under different LiDAR ray sampling constraints. On the right, we visualize our synthesized LiDAR designs under various sensor hardware constraints, which span placement, field of view, time, and sensor quantity. In experiment B, we showed that our technique is capable of generating distributed, multi-sensor LiDAR designs for robotic end effector tracking. Importantly, our designs achieve consistently improved trajectory modeling with significantly less bandwidth required, and are able to conform to the variations in scene motion. In experiment C, we show further that our computational LiDAR synthesis approach is capable of modeling and generating spatially adaptive LiDAR designs. We show in a warehouse inspection setting that this allows us to create adaptive scanning LiDARs which can improve object detection while reducing ray sampling and bandwidth requirements. In experiment D, we show that our system is capable of not only LiDAR detector design, but also LiDAR emitter design, an important feature in practice, for example, mobile scanning settings, where emitters and detectors may not be perfectly co-located. We show that we can generate new, unconventional emitter designs that are specifically shaped around a fixed detector. We evaluate these proposed emitter designs in a physically based light transport simulator and show that the various emitter designs have minimal impact on resulting face scanning quality. In experiment E, we demonstrate the importance of our ray visibility term. Specifically, we use our technique to generate distributed single-pixel LiDAR systems for end effector tracking. We show in this ablated setting that our ray visibility term helps us to sample LiDAR systems which are consistently more effective than sampled systems without the ray visibility term. These results indicate that our technique, which uniquely models, evaluates, and designs LiDARs within our 6D design space, is critical for creating physically based, robust LiDAR system configurations. Finally, in Experiment F, we demonstrate the qualitative benefits of our LiDAR design technique in a real-world capture setting, emulating face scanning under various LiDAR system designs. Specifically, we emulate our proposed LiDAR system designs for face scanning using a single photon LiDAR. We make three key observations from this real-world analysis. First, our learned designs consistently improve coverage of our target scene. Second, our concentrated sampling allows us to capture finer facial geometry features, specifically around the nose, eyes, and mouth. Third, our well-shaped time gating from our designs improves the robustness to depth discontinuities and noise, which conventional designs may be susceptible to. For the full methodological, experimental, and analysis details, please refer to our full paper and appendix. Thank you.